who is at LASP at Colorado, in particular at the Center for Integrated Plasma Studies, and she was going to be talking about the title is Laboratory Studies of Plasma Environment Near Lunar Magnetic Anomalies. So take it away, it's you.
Thanks. So my talk seems a little different topic in this room. I hope it's still interesting for some audience. So move the slide. So as we know, the moon has no global magnetic field, but there are crustal magnetic fields, also called magnetic anomalies, distributed over the lunar surface. So here's the map of the, where can I get the cursor? Oh, here. So this is the map of the surface magnetic field. You can see the strength can go up to several hundred nanotesla at the surface, and the size can be as large as hundreds of kilometers.
Could you start your webcam?
Turn your webcam on, please.
There we go.
Sorry about that. Forgot. Can you see me? So the solar wind can interact with this crustal magnetic anomalies. And the spacecraft has observed, for example, the limb shock waves, magnetic deflection and reflection of the solar wind electrons and ions, and the ambipolar electric fields due to charge separation. And in very strong magnetic anomaly regions, mini magnetospheres can form. So as a consequence of this interaction, the surface process can be changed. One is high albedo source, as shown in this image. So here, this high albedo markers. So it's mostly caused by the solar wind protons are shielded away from the surface in the strong magnetic anomaly regions. So that surface are kept fresh. It may also be related to the formation of hydroxyl, the OH. So the swirl regions have found a relatively lower OH concentration than the surrounding regions for the same reason of the solar wind shielding. And of course, there's an effect on the electrostatic dust transport. So sorry, I didn't list here. So here I divided the interaction into three modes in terms of the magnetic field strength. When the field is very weak, so both electrons and ions are unmagnetized, the small deflection can happen. When the B field is very strong and both electrons and ions are magnetized, so what happens, the mini magnetospheres can form. So what we studied in the laboratory, we studied the moderate strength B field, where electrons are magnetized, but ions are unmagnetized. So the charge separation can be significant. So in the laboratory, we studied with plasma interaction with the dipole field. So that allows us to understand fundamental physical process, and we can dig into the details of the electric fields on the surface. So this is laboratory setup. This is a vacuum chamber. It's 50 centimeters in diameter, 30 centimeters tall. And in the middle, there's an insulating surface representing lunar surface. And underneath, there's a permanent magnet. So the dipole field shown in this picture is vertical to the surface. But we actually did the parallel and oblique dipole field to the surface. So the plasma was created by a hot filament that emitted energetic electrons to ionize the gas. And we have a Lamy probe to measure the plasma parameters, and we have a EMIS probe to measure the potential distribution about the surface. So here I list a bunch of basic parameters. So basically, the balance is very small compared to the field geometry size, And the electron gyro radius is very small, so electrons magnetize an ion with higher gyro radius are unmagnetized. So first experiment we did is with the magnetic field parallel to the surface. So this is the potential contours above the surface. This is the height, and this is the radial position. So 0 is the center of the dipole. It looks complicated, and so in the vertical profile, in the center of the dipole, we see the first the potential on the surface is about 1 TI more positive than the bulk plasma. And there's also a potential minimum called potential dip at about 1/2 centimeters above the surface. So the horizontally, the potentials on the surface varies a lot along the dipole field, and the most positive potential is at the center of the dipole. So, so here this is the surface potential plot along the dipole field, and we can see there's 4 peaks, 1, 2, 3, 4, and the bottom is a cartoon drawing to show the trajectories of the ions and electrons. So the peak 1 is the electron shielding region. So what happens? The electron comes to the field and got magnetized and follow the field lines. Follow the field lines, go to the cusp. So, but ions are unmagnetized, so they go straight to hit the surface and charge the surface positively. And this potential depends on the energy of the ions. So here we got about 1 volt more positive than the bulk, but on the moon, we can expect is, so the solar wind has very high energy, 1,000 eV. So then the potential on the lunar surface in this region can charge to be very positive, and this is a very extreme charging. And the peak 2 is the electron focusing. So because the electrons follow the field lines, go to the cusp, that is a small area, surface area than the above. So it behaves like a focusing. So the electrons charge that region more negatively. And the peak 3 is we call the electron shattering. So before I talk about that, I should talk about the peak 4 first. It's the electron intercepting. So what happens when it's further out of the dipole field, the field strength weakens, and the gyro radius of the electron gets bigger. What happens is the electron follows field lines, gyrate, and hit the surface before the field line intercepts the surface. So then charge that region more negatively. So in between the 2 and 4, and the lesser electrons hit the surface. So that surface region charges more positively. And so the second experiment we did is we had the magnetic field vertical to the surface. So again, this is the potential contours. The black arrows, the field strength and field line. The white lines are field line. So again, there are 1, 2, 3, 4 peaks. The peak 1 is slightly, or say, intermediately positive. That's because the large portion of electrons are reflected due to the mirror irreflection effect in the cusp region. And the peak 2 is more negative because it's at the edge of the cusp, so mirror reflection effect gets reduced. And the peak 3, you can see the field line basically parallel to the surface. So it's for the same reason, electrons are shielded away and ions charge that region positively. And the peak 4, so the mirror reflected electrons from cusp region will be diverted into that region and charged there more negatively. So this is the detailed study of the sheath profiles in the magnetic cusp regions. So we had two magnets for this experiment, so smaller and bigger one. So the magnetic field profile shown with these squares. The maximum magnetic field strength at the surface is about the same for both magnets, and the minimum B field is also about the same. So what you can expect is the last cone, also the pitch angle, is about the same, because that depends on the ratio of B max to B minimum. So there's two profiles with the magnetic field. So they both show that the surface potential with this 2B field configuration are more positive than without field. That's because of the mirror reflection of electrons. As I just mentioned, so the last cone is about the same, so then we should expect the same fraction of the electrons be reflected. So we should get about the same surface potential in these two cases, but we didn't. So what happens is explained in the next slide. So we did the modeling work. So I list a bunch of equations. I don't want to go into all of the details. So basically, we solved the Poisson's equation. And in conclusion, what we found is the electron-electron collision plays a role to determine this potential difference. The small magnet has a smaller cusp volume, so the collision rate is higher, and that scatters electrons to the surface. So that charge the surface is slightly more negative than the bigger magnet. So then we turned the magnetic field 45 degrees. Then we got this asymmetric potential distribution. And again, you can see in some regions the charge is really extreme, very negative. So all of this experiment tell us the plasma environment near the surface and surface charging are greatly modified, and we have identified several physical processes, including the shielding, focusing, mirror reflection, as well as the non-magnetic sheaths. And we also observe this extreme surface charging regions. So what we can expect is large positive charging can happen on the lunar surface in these electron shielding regions. And this extreme charging regions can largely alter the surface process as well as the electrostatic transport. So very quickly, the future work. So we are developing an ion source. So that way we can create the flowing plasma to emulate the solar wind. This is large cross-section ion flow, 20 centimeters in diameter. So the energy is low. It's about 50 eV, but it's way lower than the solar wind. But the Mach number is much larger than 1, so it's comparable to solar wind. So we can still study similar physics. And this is so the source is basically the anode to raise the plasma potential and flow ions out, and the neutralizer to emit electrons to create the neutralized plasma flow. So the preliminary results we got is we got 11 eV ion flow. It's not perfect, but because it's broad and it's not efficient, and so it's still ongoing, and we hope in the short future we can get exciting results from this flowing plasma interaction with the dipole field. Thanks.
Thank you. Very, very interesting. So appreciate that talk, and we don't have any questions that I see online. And since we're running just a few minutes late, I think that we'll just go straight to